Givi Basishvili.
My name is Xavier.
We work at Columbia University in the chemical engineering department. Currently, I'm in NYU. I'm a student there in biochemistry major. So we're going to go through our research, which was on microbubbles. We're going to tell you what it is and explain it. All right, so what are microbubbles, right? They seem pretty harmless, they're bubbles, but I don't want you to think of it that way right now. I want you to, basically microbubbles are really tiny bubbles. 10 micrometers, which is basically this, really tiny. But I don't want you to imagine a bubble floating around and doing nothing. I want you to think of it as a capsule, like something that has space inside it and can hold things in there. So what can hold? Oxygen, genetic information, namely DNA, and drugs. And as you can see, if you have drugs in the bubble, you can use this for medicine and save people's lives. So I'm going to go through some of the purposes. Basically, one purpose for drug delivery is targeted drug delivery. I'm going to tell you what that is. So basically, the top part here, okay, look at this. That represents a vein, right? So these bubbles are flowing down in the vein, and inside them, they have drugs in there. So if a patient has cancer, let's say, right? Some of the tissue is cancerous and must be destroyed. But the drugs we use today, there are drugs that treat cancer, but they also harm healthy cells, and we don't want to do that. By using these bubbles, we can deliver the drugs only to one area. So if the cancer is, let's say, in your stomach or somewhere near there, we don't want to damage the healthy tissue, which is going to harm you. So we can only concentrate the drug delivery to that area. So what we'll do is these bubbles will be floating in the vein. We'll apply low energy sound waves, which will only make them go down on the wall of this vein, or a capillary at this point, because you would not want to burst the vein. And then we would apply high intensity sound waves to the capillary and deliver the drugs, the green dots, to a specific area. So that could be applied to cancer. What we worked on were oxygen bubbles. Mainly the bubble inside had oxygen. So the application for this is sudden lung failure that many children experience when they're born. So what we could do was put oxygen in those bubbles. And unfortunately, many patients would die because doctors wouldn't have enough time to save them and oxygenate their blood through other methods that currently exist. But by making oxygen bubbles, we can inject the bubbles directly into the blood. And as you can see right here, this is a capillary, and you can see the bubbles in there, along with the red blood cells, right here, these red dots. This is a red blood cell. When the bubble would go in, it would release the oxygen because of the temperature difference. The body is around 37 degrees Celsius, so the way we design these bubbles would be that they would be stable outside, but once they would enter the bloodstream, they would release the oxygen. Oxygen would be picked up by the hemoglobin in the red blood cell, and basically you would have a patient breathing without it actually having to breathe, and that would save a patient whose lungs did not work. Alright, so the actual bubble chemistry now, this is where it gets interesting and also confusing. So we have four main parts that make up a bubble. We have a lipid, oxygen, obviously, the water, and the peg chain for stability. Okay, so what is a lipid? Lipid is basically made out of two parts. The hydrophobic fats, which are fatty acids right here. These are mainly carbons and hydrogen, and they don't have a charge. So what that means, as the name suggests, hydrophobic. Hydro means water, phobic means afraid. So this part is afraid of water in layman's terms. So basically it's not attracted to water. And then that's due to the charge, because there's no charge. Water actually has a charge. So the top part here is the phosphate group. which has, you see the O minus right here, that has a charge, and it's hydrophilic, which means it loves, philic means loves, it loves water and it's attracted to it. So I'm going to show you later in the next slide how the actual bubble compiles together, but that's the main part, the liquid right here. The peg chain is basically the carbon part right here. It looks, the chemical formula is this, and this part just repeats a lot. And the peg chain will go on top of that and stick out. We worked on finding the correct concentration of the lipid solutions because we wanted to find how many of these lipids we would put in a liter of water. Because if we put too much, they're going to get stuck to each other and not form bubbles. If we put too little, we're not going to get that many bubbles. And the science department, the science people called intermolecular forces. This is a love and hate term used by scientists, intermolecular forces. That's actually very complicated, so I'm not going to go into that. Alright, so that's the compiled bubble. They're enlarged a lot. It wouldn't be this size because that would kill it. So you see the oxygen core is on the inside. Then you have the water. And you have this monolayer, which means a single layer of lipid. What I showed you before, this thing, this big thing, is actually like a tiny one right here, stuck there. And this forms automatically in water. When you, I'll show you how we actually engineer it, but this assembles on its own because this part, you see the fatty acids, they're attracted to oxygen because they hate the water, face inside. And the top parts face the water because they love it. This is the peg chain. This makes it more stable so the bubble doesn't disassemble. So now the actual engineering, how we made this in the lab, is this is a simple diagram. And also this is a 2D image. You should be imagining a sphere because, okay, so what we had was a machine where we had a chamber. It was a metal chamber, so you wouldn't actually see any of this. But we had oxygen flowing in from one side and lipid from the other. And the lipid would sink down because it's more dense, oxygen would be on top. But in order to make the bubble, we would apply sound waves, and the sound waves would shake the water. And when the water would start shaking, we would trap the oxygen inside and bring it in. And then we would collect this in the beaker. The size of these bubbles was controlled by the frequency. So the shorter these waves were together, the smaller the bubbles. The higher the frequency, the smaller the bubbles. This part was called by our lab like the cake. So if I refer to the cake, it means the bubbles. Alright, so these are the three components. Alright, now we're actually going to take you through the research. So Xavier is going to do that. We worked on 4 things mainly. Create stable bubbles to make them. Then determine the best storing conditions and their properties, which is important because we want to make good bubbles that don't die off soon. And then final stage would be to test them in living organisms. Alright guys, any questions before Xavier goes on? That was the intro. Okay.
You said the bubble depends on the frequency?
Yeah, the bubble size depends on the frequency. So,
the higher the sound wave, the bigger the bubble.
the higher the frequency, the smaller the bubble. So, yeah, we can't take too many questions, but yes.
You said that the hydrophilic loves the water and the hydrophobic
Hates the water. Okay, one more.